The Fundamentals of Tool Design video series, examining the diverse field of tool design materials and technologies. This program explores the fundamentals of composite tooling design. Quality tooling is a fundamental requirement for the manufacture of fiber-reinforced thermosetting polymer, or composite parts. This is due to the fact that every step in the composite part manufacturing process must be tightly controlled to ensure superior material properties and predictable performance in the final product. The use of computer-aided design, or CAD software, has allowed tool designers to create dimensionally accurate digital part, tool, and assembly files in 3 dimensions. This capability to work from the as-engineered part model has greatly enhanced the designer's ability to explore the many aspects of the part-to-tool relationship while controlling the variables specific to molding composite parts. Composite tooling designers not only have to be knowledgeable about the variety of tooling materials and their properties, they also need to be familiar with the various fiber and fabric forms, polymer resins and reactive chemistries, and the many different methods and techniques used in processing composites. Additionally, an understanding of the sawing, drilling, and machining of composites is mandatory to design good working tools. From raw material handling to material processing and assembly, well-designed composite tooling enables manufacturers to control each step of the process, resulting in more consistent part production and uniform assembly practices. Composite manufacturing methods include wet layup and spray-up, pre-preg layup, vacuum resin infusion, resin transfer molding, compression and matched press molding, pultrusion, filament winding, automated fiber and tape placement, and a multitude of variant and hybrid approaches. There are many different types of tools required to support composite manufacturing, including ply and core kit cutting templates, ply and core locator templates, layup molds or mandrels, trim fixtures, and drill jigs and fixtures. Ply and core kit cutting templates may be required to support pre-layup operations. Ply and core locator templates might be necessary to support layup of the materials in the mold or on the mandrel. These templates are usually designed to index to the mold and have machined, color-coded eyebrow cutouts along the ply or core locations to facilitate marking these locations on the laminate during layup. Detailed ply layup information is often provided on the template to aid the layup technician. Automated ply and core cutting systems and laser ply projection systems for controlling ply and core placement and orientation verification are also commonly used for many high-volume or precision layup operations. Layup molds or mandrels provide the desired shape for parts production and are the primary tools used to produce composite parts or panels. They may be a metal plate used to manufacture panels, or a more complex contoured configuration necessary to produce a complicated composite part. To produce hollow parts, cores may be used for manual layup. Cores are commonly designed to dissolve or collapse for removal from the part after curing. Nearly every composite part needs to be trimmed after molding. Provisions for trimming range from the inclusion of a knife flange along the net trim edges of a layup mold to designing a separate, more complex trim fixture or jig that locates and holds the part in position for processing. These tools may also be used for automated processes such as water jet cutting and CNC routing operations. In this case, the tool may only serve as a holding fixture for the part to be located relative to the machine for the automated cutting or trimming operation. Drill jigs or fixtures are typically required to secure and support a composite part and assist in accurately guiding a drill to produce a hole. Drill jigs commonly utilize slip renewable bushings to minimize tool wear and subsequent rework. There is a wide variety of materials used to create composite tooling, with some of the most common being glass-reinforced polyester or vinyl ester laminated tooling, carbon or glass fiber reinforced epoxy or Bismaili imide laminated tooling, Invar-coated carbon fiber reinforced tooling, and steel. The choice of one material over another for a given composite tool may be determined by two factors: the part production quantities required over the life of the tool and the upper service temperature that the tool has to withstand during parts processing. The service temperature is of concern because a material expands when heated, altering its dimensions. The value given to a material indicating how it reacts during a change in temperature is referred to as the coefficient of thermal expansion, or CTE value. A high CTE value indicates a material expands a lot under elevated temperature, while a material having a low CTE value expands less. Glass-reinforced polyester or vinyl ester laminated tools have a very low temperature capability and typically are used for room temperature molding. Carbon or glass fiber reinforced epoxy or Bismaili imide laminated tooling can easily service up to 350 degrees Fahrenheit or 177 degrees Celsius. Other metallic tooling materials, such as Invar alloys and steel, can also easily reach that temperature. Carbon fiber reinforced epoxy or Bismaili imide tools have a low CTE value and are very lightweight, having a density of around 1.4 grams per cubic centimeter. Because they are lightweight, carbon molds and fixtures are typically quicker to heat and cool than metal tooling. Glass fiber reinforced epoxy or Bismaili imide tools are significantly heavier than carbon tooling, with a density around 2.1 grams per cubic centimeter. These tools are also thermal insulators and have a significantly lower modulus or stiffness than carbon, requiring approximately 3 times the laminate thickness to match the stiffness of carbon tooling. Invar, which is a nickel-iron alloy, is an ideal metal for designing high-temperature molds, mandrels, and fixtures since it has a low CTE value in the same range as carbon fiber reinforced tooling. The downside is that Invar is extremely heavy at 8.12 grams per cubic centimeter and requires more energy and time to heat and cool. Invar comes in rolled sheet stock that can be formed, welded, and machined, or can be cast and machined to shape. Invar-coated carbon fiber reinforced tooling has emerged in the past few years to provide a lightweight, hard, low expansion, vacuum integral surface on a composite tool. This material combination can provide longevity to an otherwise limited tool life of a carbon fiber reinforced plastic tool laminate. Steel can be useful for many applications, but it is nearly as heavy as Invar, while stainless steel is a preferred material for molding and resisting oxidation. It is not very economical. Depending on the alloy, steel can weigh in at between 7.86 and 8.02 grams per cubic centimeter and has a fairly high CTE value. There are many things to consider when designing tools for the variety of composite manufacturing processes. While many common tool designs are used for post-molding operations, actual mold or mandrel designs differ considerably depending on the processes that they are designed to serve. The primary tooling requirements for molding fiber-reinforced plastic parts are that provisions be made for the layup, compaction, and curing of the parts. All mold and mandrel designs should allow for sufficient draft angle so that the cured part can be removed from the tooling after the molding process. With complex geometries, this might mean using multi-piece tools. Additionally, a combination of inner surface fiber tension and resin shrinkage contributes to spring-in of composite angles made at elevated pressures. Spring-in is addressed by adding to the angle requirement of a composite tool. Typically, 1/2 to 2 degrees of correction is required, depending on the specific angle, radii, and the materials and processes being utilized. A layup mold used for hand or contact layup with no vacuum bag or elevated temperature cure requirements might be designed to simply control the part shape and net dimensions at room temperature. The material selection for this type of mold is broad, since the tool does not need to see elevated temperatures or maintain vacuum integrity throughout a process. Any material such as wood, tooling board, foam, metal, or composites may be utilized for a mold of this type, and may be chosen more so on the surface quality requirements for the end part than on any other process considerations. On the other hand, a layup mold designed for vacuum bagging and elevated temperature pressure processing requires careful material selection and perhaps special dimensional offsets to mitigate the effects of thermal expansion. Single-sided molds designed for vacuum infusion processing, or VIP, and vacuum-assisted resin transfer molding, or VARDM, utilize a flexible vacuum bag. These molds commonly require additional flange area outside of the part area to support placement of the vacuum seals and/or resin injection plumbing. Some designers may choose to provide channels and troughs or even built-in plumbing to facilitate these needs. Vacuum and service temperature requirements drive the material selection for these types of molds. Often, two-piece infusion molds may be designed with a solid outer mold half and a flexible inner mold half, with silicone rubber seals to vacuum down the inner tool and clamp it in place prior to the infusion process. Molds for resin transfer molding, or RTM processes, are typically designed to resist medium to high internal hydraulic pressures. These tools are designed with two main considerations in mind. First, properly securing the dry preform to prevent hydraulic washout. And second, adequate placement of resin inlet sprues with plenty of vents to produce a proper resin flow pattern. RTM tools are built much like matched die sets and can be used within a platen press to help offset the internal pressures. RTM tools can be made from composite materials, but are normally made from selected metals. Heating and cooling systems are often integrated into the design of these molds to facilitate resin curing. With RTM and VARDM or VIP tooling, it is important to design simple, replaceable hardware that incorporate pass-through sleeves or other features that allow for tubing and low-cost inserts to be removed and replaced between runs. Tooling and mandrels for automated fiber placement and tape laying processes typically are designed to provide the appropriate innermost loft or outermost loft surface. Tools and mandrels of this type may be designed to index on an automated trunnion or machine bed platform for use with automated fiber placement and tape laying equipment. Pultrusion machines are designed to collimate pre-tensioned fibers, stitched mat and/or continuous filament mat, introduce resin to saturate and impregnate the materials, and process or cure these materials into a constant cross-section through a highly specialized die set and machine molding process. These designs often cross over into the machine design category as they are typically used for molding a specific shape in high-volume production. Pultrusion dies range from single-piece dies to multi-piece dies and have a floating or movable segment such as an internal mandrel to produce hollow parts. Pultrusion dies are most commonly made of a mold steel such as P20 tool steel. Pultrusion dies commonly integrate heating and cooling systems to facilitate curing of the composite materials. Many times, the pultrusion machine will include a cut-off saw to cut the processed pieces to specific lengths. When molding a composite tool laminate, a master or part model is required that is the opposite gender than that of the final mold. This model must include all of the various part features, flanges, and indexes that must be molded in the final laminated tool. In an effort to minimize the effect of thermal expansion when molding the tool laminate from the model, designers tend to select materials that can be cured at low temperatures and then post-cured to perform at higher temperatures in service. With all composite tools, not only is the laminate design important to the performance of the composite tool, but the workmanship, materials, and process that go into the actual laminate fabrication are of utmost importance to the quality and longevity of the product. The goal of any manufactured composite tool laminate is to achieve a high fiber to resin ratio with a very low void volume, preferably less than 0.5%. In addition, the tool surface must be just resin rich enough so as to not have fiber print transfer to parts produced from the tool. Many chop spray glass mat reinforced polyester and vinyl ester tools with heavily gel-coated surfaces almost always exhibit cracking in the gel coat after a few runs. This must be repaired by removing the cracks and bubbles in the damaged areas and repairing them with a mixture of milled fiberglass and gel coat. If the composite tool requires a support structure, then the tool designer is tasked to design a torsion-resistant substructure and/or a frame that will provide a rigid platform for the tool laminate to sit on during part layup and processing. For elevated temperature service, these substructures are usually made from the same material as the parent tool, but can also be made from dissimilar materials such as steel, Invar, or aluminum. When a tool is not going to be subjected to elevated temperature, then dissimilar materials such as steel tubing can be used to produce a cradle or substructure to reinforce the tool laminate. Often, with very large tools, these structures can be adapted to a trunnion so as to allow the mold or fixture to be rotated into the best working position. In addition to tooling support, transportation and handling features must also be considered part of the tool design. Tool lift lugs should be positioned in such a manner so as not to allow the lifting straps or chains to load or damage the tool. For large tools, forklift provisions should be designed so as not to allow the forklift tines or rails to contact or damage the primary tool body or laminate.